Hello students, welcome to Inside Physics. Today we will discuss about the Clausius Mossotti equation. This equation is relating the electronic polarizability and the dielectric constant of a dielectric material. This equation is a very good one for further study of dielectric materials. So how we proceed to derive a mathematical form of Clausius Mossotti equation. So first of all, take an elemental dielectric material sample which shows only electronic polarizability. We all know that the electronic polarizability is the major contributor out of all other four polarizations which we have discussed in our previous videos. So here the polarizability is a degree of polarization that happens due to all the individual dipole moments of the atoms or molecules or ions because of the external applied electric field. So this is how we proceed with the basic details. The fundamental details are, first of all we need to take a sample of a dielectric material which is of a single element, and what are the elemental things we know. Generally this silicon and germanium are elemental solids. Here the electronic polarizability is given by P by N E I. We will know the terms here. P is polarization due to all the atoms. N, number of atoms per meter cube. So here N is number of atoms per meter cube. You can take it as per unit volume. Here EI, this is the internal electric field which we have calculated as Lorentz internal field. In our previous video, that video already I have taken previously. This is the internal field which is also called Lorentz field inside a dielectric material that will exist when we apply an external field to a dielectric material. For that we know EI, the internal, the Lorentz field is equal to E plus P by 3 epsilon naught. So where epsilon naught is the permittivity of free space. With this we can proceed, and alpha E here is written as P by N, and EI, this is taken into this brackets E plus P by 3 epsilon naught. Okay, so we all know that the polarization is nothing but epsilon naught into psi into external field. This we all know, where psi is the susceptibility of a particular material. This polarizability and susceptibility depends on the nature of the materials. So here we all know that psi susceptibility is equal to epsilon r minus 1. So that relative permittivity minus 1. With this we can write epsilon naught minus epsilon r minus 1 into E. So E is equal to P by epsilon naught epsilon r minus 1. So this E value will substitute here. So this becomes alpha E is equal to P by N into so we'll substitute the term here. What is E? P by epsilon naught epsilon r minus 1 plus p by 3 epsilon naught. Okay, substituted this e from this. Okay, now how we will get the next term here? I will write here alpha e is equal to c. Here this n will go to the left hand side. Okay, so then we will get n alpha e is equal to n will move to this side, and this p, the p value is taken outside. So p is taking a common factor here, that will become p by epsilon naught epsilon r minus 1 plus p by 3 epsilon naught. So this is what we got. Here p and p will be getting cancelled. This p and p will get cancelled. So alpha e is equal to, so if you observe, take the epsilon naught out of these brackets as a common factor, and what happens, this epsilon naught will move to the numerator. After taking the common factor, this p and p will be getting cancelled. So this equation will become, taking the epsilon naught to the numerator, this will become 1 by epsilon r minus 1 plus 1 by 3 epsilon naught. Okay, so here further moving to the next steps, this epsilon naught will come to the left hand side. So this will become n alpha e by epsilon naught is equal to, here see, this one is coming to the left hand side and into the denominator. Here what happens, we will take the LCM here. So if we take LCM, this epsilon naught is also moved outside, right? Epsilon naught moved to the other side. So 1 by 3. Here the common factor is the LCM I have taken. So here the above terms will become, after taking the common factor, just observe this, into the denominator I need to write. First of all, I will take the LCM, epsilon r minus 1 into 3. So this will become 3 minus, see, epsilon r minus 1, right? So here if you observe, this will become epsilon minus of 3, and here I will write it as plus. Okay, what is the LCM here we are taking? If you redistribute these terms, this will become epsilon r minus 1 plus 1 by 3. So this term goes to the numerator. So here this epsilon r minus 1 goes to the numerator. Three plus epsilon r minus 1, what we can write here? This minus 1, 3 minus 1 will become 2. Okay, so here I will write epsilon r plus 2. Okay, These are the terms. So here this has become to be like this. So the final equation from this, what I am writing here, I am writing, look at this, n alpha e, this 3 will come to the left hand side and into the denominator, which will become n alpha e by 3 epsilon naught is equal to, see here, epsilon r minus 1 by epsilon r plus 2, epsilon r minus 1 by epsilon r plus 2. This is what the Clausius Mossotti equation will be. So we can finally write the equation as is equal to n alpha e by 3 epsilon naught. So this is the Clausius Mossotti equation, which relates the dielectric constant with the polarizability of all the atoms in a dielectric material. So this, by calculating with this equation the dielectric constant of some materials like diamond, silicon, germanium, which are fourth group elements in the periodic table. So for diamond, the dielectric constant will come to be 5.68. For silicon, this will come to be around 12. For germanium, the value will come to be as 16. These are the dielectric constants calculated with this equation. So this Clausius Mossotti equation is only applicable for non-polar solids which is having a cubical crystal structure. So that is the limitation of this equation. So this is about Clausius Mossotti equation. We will come with some more topics in dielectric materials in the next video.